Hello guys, welcome to Physics Grad. Today we are going to learn about what are known as the envelope equations, which defines uh, the equation of the envelope of a family of curves. Okay, so to understand this better, let us first define or understand what do we mean by an envelope. Okay, so um, what do we mean by an envelope? Okay, so I am going to define it in this manner. It is a curve, right, which touches a family of curves, or surfaces. Okay, so it is curve or surface. So family of curves or surfaces at exactly one point, that too tangentially to each curve. Okay, so what do we mean by this statement? So this means if you consider, let's say, some curves of this form, like this, say, okay, then I can draw a curve in this manner which touches each of these curves at exactly one point, that too tangentially. Then this will give us the envelope. This curve is called the envelope, and these curves are what we called as the family of curves. Okay, I'm going to define this more formally very soon. Another example would be if you consider let's say a ladder, okay, which is sliding along this wall in this manner. So the length of the ladder is fixed. Okay, so as it slides down, it goes like this. Correct? And it was like this, so on. So this forms a curve like this. Okay, so this is further along like this, so on. So this curve here, okay, which touches every line at exactly one point tangentially, will be the envelope in this case, for wherein the family of curves is nothing but the family of these straight lines whose length is fixed between its x and y intercepts. This is another example. Okay, one more example would be, let's say, these family of curves that are basically circles whose origin is shifted along, let's say, x-axis. Okay, then this also forms a family of curves, and the envelope for this would be this one. These two lines, both of them form the envelope because they touch the circles at only one point, and that too tangentially. Okay, but there are also cases wherein the envelope need not exist. So for example, family of concentric circles, if you have these infinitely many circles, there is no way to draw a curve which touches all the circles tangentially at exactly one point. So in this case, envelope doesn't exist. Envelope doesn't exist. Okay, so I hope that this clears up the meaning of envelope, at least in an intuitive manner. Okay, so moving forward, the next question would be how to represent the family of curves. Okay, So how to represent the family of curves? So for this, let us consider. So consider an equation given by some function of x, y and alpha is equal to 0. Okay. Now here x and y are variables, which in some manner define the shape of the function. Okay. And alpha is a parameter. Okay. In physics, usually we come across these kinds of equation wherein these variables are either time, position, velocity, acceleration and so on. Okay. And these parameters are often the mass or length of a rod or value of capacitance, inductance, etc. Okay. So usually our equations of motions depend on these things, and the system is characterized by these things. So the parameters characterize the system. Okay. So changing the parameters is going to change the shape of the curve, which is defined by these variables. Okay. And that results, so for different values of these parameters we get different curves, and these sets of curves form what is known as a family. All right. So let us make it more clear. And so what I was saying is that by varying alpha, okay, the shape of y as a function of x. Okay. So in this particular equation, I can always write y as a function of as a function of x and alpha, but I'm saying alpha is a parameter, and the equation which defines in our case the physical motion or some phenomena will be mainly dependent on the variable, and alpha is fixed for a system. Okay. So that means usually we will be dealing for a fixed system with only y of x. But in case the parameter of the system changes, then this relationship is also going to be altered in such a way that the shape of this y of x is going to change. Okay. So for example, if you have let's say x square plus y minus alpha the whole square is equal to r square. Okay. This is basically representing a circle whose origin is in the y-axis with the coordinates 0 and alpha. Okay. So for a fixed alpha, our relationship between y and x is basically this curve. Okay. If alpha changes, the origin moves and the curve also changes. Okay. But in a sense, the shape of the curve is remaining the same. Okay. And by the shape of the curve, I'm talking about the behavior of the system. Okay. Of course, it is influenced by alpha, but you see that the curve in this particular example, the curve has been just shifted. Okay. So the value of alpha or the parameter actually controls either the position of the curve or the shape of the curve and so on. Okay. And in the equations that we usually encounter, these parameters are kept constant, and so we get only y of x. But in case we change alpha also, for alpha 1 we get y of x, for alpha 2 we get another y of x. These two y of x will differ. Okay, that is what I am telling here. Okay, so that is the meaning of this statement. By varying alpha, the shape of y equal to y of x will change. Okay, so by changing the shape, it can either change its geometrical form or structure, or it can be shifted by some amount, as we saw in the case of our example, and so on. Okay, so by varying alpha, the shape of y equal to y of x, uh, changes. Okay, usually, but not always, smoothly. By this, what we mean here in our case, this example, this is a smooth transition because for a small change in alpha, the circle also translates by a very small amount. Okay, so if you make alpha as small as possible, the shift in the circle also becomes as small as possible, and therefore the variation is smooth with respect to alpha. But it need not always be the case. Okay, there may be some cases wherein the changes may be sudden. Okay, but most of the times this is the case. Okay, and in the examples that we are going to consider, we are going to say it very smoothly, just so that we get the intuitive feeling, or we get the we are able to understand what's really going on, and putting into consideration the fact that uh, it need not always be a smooth transition is just going to be a generalized case, and which is not encountered as often. Okay, but in order to understand, this is not needed. If we can understand this, we can later on move into understanding what happens when it doesn't vary smoothly. Okay, so for now we are going to stick with functions which vary smoothly when alpha changes. Okay, so our family of curves will be given by f of x y alpha 1 equal to 0, f of x y alpha 2 equal to 0, f of x y alpha 3 equal to 0, and so on. Okay, so these will represent the family of curves. Because for each of these alpha 1 alpha 2, for each alpha I, we get a curve y equal to y of x. Okay, and by varying alpha I, the form or the structure of this curve is going to change either in shape or get shifted in space, or both. We don't know. Okay, all right. Now, how do we find the equation of the envelope for this family of curves defined by these things? Okay, so the question is how to find the equation of the envelope. Okay, and as we formally define this, I am going to side by side give you one particular example so that we understand it better. And our example is going to be that of a family of circles whose origin gets shifted along the y-axis. So our family of curves is going to be x square plus y minus alpha the whole square is equal to r square, which means if I have to write it in this form, I will write it as x square plus y minus alpha the whole square minus r square equal to 0. Okay, so this gives the family of curves, in this case the family of circles whose origin is along the y-axis and shifted by alpha. All right. Okay, so how do we find in general the equation of the envelope for a family of curves given by x, y, alpha equal to 0? Okay, so to do this we will consider the following. Okay, all of these curves can be represented in 3D space defined by the coordinates x, y, alpha. Okay, in 3D space defined by the coordinates x, y and alpha. So the curves can be represented in this space as a surface defined by the equation f of x, y, alpha equal to 0. So what do we mean by this? Okay, so let us first draw our 3D space, that is alpha, x and y. All right, so let me extend this to the negative side as well. So that will be our negative side. Okay, now our example of the family of curves was x square plus y minus alpha the whole square minus r square equal to 0. Correct? Here r is kept constant. Okay, this is constant. We are going to only vary the parameter alpha. Okay, now f of x, y, alpha in this case is equal to x square plus y minus alpha the whole square minus r square. Okay, if I choose randomly any x, y and alpha, I will get some point in this 3D space, and that point will correspond to the value of the function f given by this particular expression. For example, if I choose alpha x as 1, y as 1 and alpha as, let's say, 2, okay, then the f of 1, 1, 2 will become 1 plus 1 minus 2 the whole square minus r square. Okay, let us say r is equal to 1 to make it simpler. So this will become 1 square, which is 1. So this is equal to 1 plus 1 plus 1, 1 plus 1 minus 1, which is plus 1. Okay, so every point in this three-dimensional space will correspond to some value given by this expression, which is this expression. Okay, but our family of curves is represented by those points in this space where this expression is equal to 0. Okay, so our family of curves corresponds to f, x, y, alpha equal to 0. So not all x, y, alpha in this 3D space will satisfy this condition. Only some subset of this 3D space is going to satisfy that condition, and that is going to be, all those points which satisfy this condition is going to be a surface in this particular 3D space. Okay, so our example here, the surface is going to be a tilted cylinder, okay, which is of this form. So it will look something like this. Let me use a different color. Okay. So this is going to be the surface in our case of family of circles, the example that we have taken. Okay. So all the x, y, alpha which lie on this surface, which is defined by this equation, this is equal to 0, is going to be part of the family of curves. Okay. So this means if I choose any alpha, let me use a different color. Let's say I choose this alpha naught, I'm going to call it. Then corresponding to this alpha naught, okay, corresponding to this alpha naught, I am going to get this particular circle whose center is 0 comma alpha. Okay. So why? Because alpha naught. If I choose a particular alpha naught, okay, then this equation becomes the equation of a circle in the xy axis whose, so this is going to be the curve, okay, that is the y equal to y of x curve for alpha equal to alpha naught. Okay, and that curve is basically the projection of this particular section of the surface by the plane represented by alpha naught. Okay, and projection of that section on the xy axis will give the curve y equal to y of x corresponding to alpha equal to alpha naught. Okay, I hope that this is clear. Now if you consider, okay, now if you consider alpha 1 and alpha 2 equal to alpha 1 plus h. Okay, so in our case, let me draw this again. It is going to look something like this: alpha, x and y, and our surface is going to be like this. Okay, so this is not there. Now I am going to choose a particular alpha 1 and alpha 1 plus h. So this is going to be our h, and corresponding to this we are going to have this particular section whose projection in the xy plane is going to look like this, and the section defined for this particular alpha 1, its projection is going to look something like this. Okay, so in our xy space, x, y, we are going to have these two circles, that is, this is the one of them and this is the other. Okay, I'm basically drawing these two circles here, the projection in the xy plane. Now this, if you notice, intersects at these 2 points. Okay, and our envelope can either be here or here, and let our envelope touch these two circles at these 2 points. Okay, so I'm going to call this point as P1, this point as P2, and this point as P. That is the point of intersection as P. Okay, so the surfaces f of x, y, alpha 1 equal to 0 and f of x, y, alpha 2 equal to 0 intersect at P. Okay, and envelope touches f of x, y, alpha 1 at P1 and f of x, y, alpha 2 at P2. Okay, and that is what I have shown here. Now if you take the limit as h tends to 0, what is going to happen? So as h tends to 0, P is going to coincide. Okay, so P will coincide with P1. So why? So what I'm saying, as our h goes to 0, okay, these 2 points are going to come closer and closer, which means these 2 circles are going to come closer and closer. Okay, this in turn means P1 and P2 are going to become closer and closer, and since P is in some sense between P1 and P2, it also implies that this P is going to come closer and closer to P1, and as it goes to 0, that is h goes to 0, all the 3 points P1, P2 and P are going to coincide at P1. Okay, so that is intuitively straightforward. Okay, so let me write that down. So this is because P always lies between P1 and P2, and as h tends to 0, P2 will tend to P1 because the two curves tend to become the same curve when h tends to 0, because the value of alpha and alpha 2 become very close to the same value. So since P lies in between, now this is a tricky thing to say because this is not mathematically rigorously a mathematically rigorous statement. This is an intuitive statement. Okay, and we don't need to go into such mathematical rigor in this case because we are just trying to understand what is happening, and this intuitive feeling is more than good enough. Okay, so as h tends to 0, P2 tends to P1, and since P always lies between in commas between P1 and P2, see when h tends to 0, P2 tends to P1 implies P tends to P1. Okay, all right. Now what I want you to do is I want you to imagine. Okay, so now imagine a perpendicular line drawn from P to the XY plane. So what are we doing? So if we go back to our picture here, our point P corresponds to this point. Okay. So let me draw this again for clarity. We have alpha X and Y, and this is going to be our surface. Okay. And our two circles were like this and like this. So this corresponds to this, and this corresponds to this. Okay. Now what I'm going to do, I'm going to draw a perpendicular from this point in this direction. Okay. Now if you notice, this point is going to meet this line is going to meet the surface at 2 points. One over here and the other over here. Okay. And it doesn't touch the surface at any other points. So to imagine this better, you can imagine a water bottle or some cylindrical object, and this particular line as some kind of a pin, and you poke it at one particular point, that is this point, then you will realize that it will come out of the cylinder from some other point, but it can only go through 2 points in the surface. Okay. All right. So I hope that you get what I'm trying to say there. So what I'm trying to say is the following. This line touches f of x, y, alpha equal to 0. This surface at alpha 1 and alpha 1 plus h. Okay. Now remember, I'm going to call, to be more clear, we are going to call the x and y coordinates of point P. So this particular point, I'm going to call this as xp, yp. Okay. So when we draw this line, we are keeping the x and y constant. Okay. So and x and y equal to xp, yp. This is kept constant. So the point of intersection of this line with the surface happens at xp, yp, alpha 1 and xp, yp, alpha 2. Alpha 2 is nothing but alpha 1 plus h. Okay. The points, so this line is defined by a set of points, right? What are those points? So those points corresponds to all the values of on this line. So line is defined by points xp, yp and alpha, where alpha is ranging from minus infinity to plus infinity. Okay, alpha ranging from minus infinity to plus infinity. So this is how the line is defined. But in between these 2 points, okay, how do we define the line? So the points xp yp alpha, where alpha belongs to the interval alpha 1 to alpha 2, okay, in the alpha line, do not lie on f of x y alpha equal to 0 surface. Okay, so these points which are in between the point of intersections do not lie on the surface where f of x y alpha equal to 0. That means the value of the function f of x y alpha is going to depart from 0 as we move along the line from here to here. Okay, that is what I am trying to say. So we have therefore f of x y alpha is not equal to 0 along the line when alpha is in between alpha 1 and alpha 1 plus h. Okay, now consider Rolle's theorem. What does this theorem say? This says that if f is continuous in the interval a b and differentiable in ab, and if f of a is equal to f of b, this implies there exists a c belonging to the interval closed interval ab such that f dash of c is equal to 0. This is what the familiar Rolle's theorem says. Okay, now we are going to apply this Rolle's theorem for this function. Okay, and what is the justification for that? The justification is as follows: f of xp yp alpha 1 is equal to f of xp yp alpha 2 is equal to 0. Okay, we are going to keep x and y constants and we are going to vary alpha. So this implies there exists some alpha dash such that f of xp yp alpha f dash of xp yp alpha dash is equal to 0. Okay, now any alpha which lies between alpha 1 and alpha 1 plus h can be represented as alpha dash is going to be alpha 1 plus theta times h, where theta is less than 1 greater than 0. As theta varies in this manner, we are going to go from alpha 1 to alpha 1 plus h. So there exists alpha dash implies there will exist some theta where this particular condition is going to be satisfied. Okay, that is what Rolle's theorem is saying, because along this line we are going to look at all the points xp yp and alpha. Okay, but in this interval, that is alpha 1 to alpha 2, if I were to plot this particular value of so if I were to plot this f of xp yp alpha versus alpha, then at alpha 1 and alpha 2 the value is 0. Okay, and in between it can be anything. And what Rolle's theorem says is that there exists some alpha dash. Okay, let me draw it like this. Some alpha dash where the slope of this particular curve is going to be equal to 0. And this slope is defined with respect to alpha. So you have to differentiate with respect to alpha. Okay. So this is same as saying that therefore we have there exists some theta such that f dash of xp yp alpha 1 plus theta h is equal to 0. Okay. Now if we apply the limit as h tends to 0, this condition will tend to f dash of xp yp alpha 1 equal to 0. Okay. So finally what do we have? So this is the condition for what? So let us write that. So two conditions that must be satisfied for the envelope to touch P1 are. Okay. So as you apply the limit h tends to 0, our point P is going to go to P1. Okay. And this actually becomes xp1 yp1 when the limit as h is tending to 0. Okay. So for any x and y, okay, or not like this, for any point xy that is lying on the curves, family of curves, and on the envelope. In our case, an envelope, okay, must satisfy for any point x and y that is lying on the curves and the envelope, which is nothing but the point of contact, should satisfy two conditions. Which are those? The first one is of course f of x y alpha must be equal to 0, and the second one is f dash with respect to alpha, which is nothing but dou f of x y alpha by dou alpha should be equal to 0. Okay. When for a given alpha, when these two conditions are satisfied, then the corresponding x and y values are going to be the same as that of the coordinate of the point which lies on the family of curves as well as being touched by our envelope. Okay. So which is in our particular case was P1. Okay. So in general, for any alpha, that particular point P1 should satisfy these two conditions. Okay. And from these two, we can eliminate alpha. Okay. And when we do that, we will be left with some relation between x and y. Okay, so let me make some space here. So we will be left with some relation. So when we do this, we will have a relation y as a function of x, okay, which satisfies these conditions, and this is going to give us the equation of the envelope. Okay, so to understand this better, again we will use our example of concentric circles. So let me make some space here. Oops. So in our case of concentric circles, what will we have? We have that x square plus y minus alpha the whole square minus r square equal to 0, and if and for x y belonging to the envelope, the following must be satisfied, which is first f of x y alpha equal to 0, which means that is same as this condition, and second dou f by dou alpha of x y alpha equal to 0. This implies when I differentiate this equation with respect to alpha, which means I have to keep x and y constant, I am going to get 2 times y minus alpha into minus 1 equal to 0. This implies alpha is equal to 1. Substituting this back here, I am going to get x square plus y minus alpha is equal to y. Okay, alpha is y minus y the whole square minus r square equal to 0, or x square is equal to r square, which implies x is equal to plus or minus r. Okay, so what this is saying, this is the relationship for all the points which belong to the envelope. Okay, and we can easily verify this, because if you take these sets of circles like this, the envelope is going to be these two lines given by this point is basically this distance is basically r. So these lines is either x is equal to r or x is equal to minus r, which forms the envelope for our example. That is the equation of the envelope. Okay, and that is what we have got here. So to summarize, if we have a family of curves represented by f of x y alpha equal to 0, then to find the equation of the envelope, all the x and y points which lie on the envelope must satisfy these two conditions, and from these two conditions we can eliminate alpha and find the relationship between x and y which are lying on the envelope curve, and therefore we will get the equation of the envelope. So that is the procedure to calculate the equation of the envelope. Okay, so yeah, that's it for this video. Thank you for watching. See you next time.